Okay, now I'm going to put all of those cost curves together. This is going to, some of these graphs begin to look a little complicated, but there's some insight that comes out of this. So let's work on this. So we note that marginal cost is upward sloping because of diminishing returns. That is, as you add more and more of each variable input, each additional unit is adding less output than the unit before. So that's why we call it diminishing. The average variable cost is upward sloping because of that, but it's going to be flatter than the marginal cost curve. Average fixed cost will be downward sloping because of the spreading effect. And something else is going to be true is that the marginal cost will intersect the average total cost from below and cross it at its lowest point. And here we see that illustrated. So looking at Selena's salsa, here's the marginal cost curve that's upward sloping. Here's the average fixed cost that's downward sloping. Right, as we increase output, we spread that overhead over more cases. And then the average variable cost curve is upward sloping. An average total cost, if we put the variable and the average fixed cost together, we get this. And we see that the marginal cost crosses the average total cost at the minimum point. So that's what we stated before. And the reason is, you can think about this, if the marginal is below the average, then each additional case that you make is going to bring the average down. And if the marginal is above the average, then it's going to pull the average up. You could also think about this, right? If we had the average height of people in the classroom is 5 feet 10 inches, and the next person who walks in is taller than 5 feet 10, that raises the average in the room. If the next person who walks in is lower than 5 feet 10, that would lower the average in the room. And so, again, like I said, if the marginal is above the average total cost, then the average total cost is increasing. If the marginal is below the average, then that's going to be bringing the average down, and they'll cross at the point where average total cost is minimized. So we could think about this. In the beginning, specialization leads to lower marginal cost. But then at some point, we'd see that the average variable cost would rise. So for examples that we've had so far, we had variable cost increasing starting from the beginning. But a more realistic one might be that the average variable cost decreases in the beginning and then increases. So let's say that we're running a McDonald's restaurant. If we have one worker, that one worker has to work the cash register, cook the burgers in the kitchen, work the drive-through window, get the soda. If we added 2 or 3 workers, we're going to get more output per worker because someone specializes, does the kitchen work, someone does the register, somebody does the drinks in the drive-through window. So it could be that in the beginning variable cost is decreasing, and then after some point it increases. And then that would imply that the marginal cost curve crosses average variable cost at the bottom. The examples that we saw with Selena, we didn't show it that way. But this might be a more realistic representation of what would happen in the real world. Now, as we said earlier in our definition, all inputs are variable in the long run. So that means that the size of the factory may vary. And so now here's where looking at average total cost for different size factory can come into play. If you know you're going to do a small amount of business, you would build a small factory. If you're going to do a big amount of business, you'd build a bigger factory. And so we want to look at that relationship. Okay, so now let's look at Selena. She has here 2 possible different size of stores that she might be running. So one ATC1, so that's average total cost if she's in the small store. So it has a lower fixed cost. ATC2, that has a high fixed cost. That's a bigger store, so she's got bigger rent she has to pay. So if she's only producing a few cases per month, the small store is better because her average total cost is smaller. But once she gets past 4 cases, then her cost is lower per case, if she goes with the bigger store, the higher fixed cost. And so this will be important now to think about what is the optimal facility size. Knowing what the volume is that you'll be producing, should you invest in the small facility or the large facility? And here we see the numbers that the fixed cost here is 108 for the small store, 216 for the big store, and so that means that the average total cost is initially lower for the small facility, but once the output gets big enough, then that larger facility is justified and has lower average total cost. And so now I want to talk about the long run average total cost curve. What we're looking at a moment ago was talking about the short run, where we had fixed costs and then looked at how average total cost varied as our variable inputs changed. But now what we want to look at is what's the optimal size in the long run. So here are, we could look at three different curves here. So here we have ATC3. So this would be low fixed cost. ATC6 is this curve right here, BCY. This shows medium size facility, so it has medium amount of fixed cost. And then ATC9, that says the largest facility has the highest fixed cost. So if Celina is producing only 3 cases per month, or even 4, that the smaller size facility gives her the lowest average total cost, right? Because ATC3 is below ATC6 all the way up till we get to near 5 cases per month. If she's producing between 4.5 and 7.5, then ATC6, this curve right here, has the lowest average total cost. And if she were making 9 cases per month, this facility size would have a lower average total cost than the medium size one would. So in drawing the long run average total cost curve, that's this blue line, which I did not mean to move, runs right along the bottom here and is tangent to the short run average total, to those different average total cost curves. It's sketching out the optimal amount of capital, optimal fixed cost for any given volume of output. So you can imagine we've only drawn 3 discrete sizes here for possible facilities, but you can imagine that there were infinite number. Like she could have a store that's 1,000 square feet, or 1,100, or 1,200, or 2,000. So we could have an infinite number of these average total cost curves here. And that's what this blue curve represents. If she could have a slightly bigger investment, slightly bigger store, that this would be the optimal point to be at, which would have slightly more capital than ATC3. Now, if she only has discrete choices, choosing between 5 different facilities she's going to rent, then you just would look like this, just have those 3 or 5 sketched. But the idea is the average total cost curve runs along the bottom here, and it's tangent to each of these average total cost curves related to one facility, and we would identify the optimal size facility. So, and in this range, we would call this increasing returns to scale. As the size of the facility increases, her average cost decreases. That's what that blue line's showing. And then over this range, say from A to X, it's constant cost. That as the output increases, the average total cost stays about the same over this range. But once we get past 9, then we have increasing cost. So there's diminishing returns, decreasing returns to scale, increasing average cost over this range. And that's what I just went over. So we also call increasing returns to scale economies of scale, because it says as your scale gets larger, it's more economical. Decreasing returns to scale we call diseconomies. As your scale gets larger, it's less economical. And then constant returns is when long run average total cost stays constant as output increases. And we'll work these examples in class, and this should help to give you some insight into what's going on.